Let us now take a few steps into fractional factorial designs. I'm going to illustrate that with reference to a system where we have three factors A, B, and C. So what I've done here on the slide is I've drawn a table, and in the columns A, B, and C, what I have done is I have listed the settings for a full factorial design. So A column in the standard form will have entries like -1 plus 1, -1 plus 1, -1 plus 1, -1 plus 1. B will be -1 minus 1 plus 1 plus 1, followed by minus minus plus plus, and C will be 4 minuses followed by 4 pluses. So this is what is called the standard design or standard matrix representation of a full factorial design involving three factors. Now in the fourth column, I have included the value of A, B, and C corresponding to each experiment. For example, you understand why this is -1. This is -1 because if you take A, B, and C corresponding to experiment number 1, if you multiply the 3, you will get -1. Similarly, this is +1 for the same reason. +1 multiplied by -1 multiplied by -1 will give us +1. So we understand how we generate this column ABC. And in the last column of the table, what I've done is I've again used the standard representation. When all the three factors, in this case A, B, and C, are low, that means -1, we represent it using that notation brackets 1. It means all the factors are at the low level. And this is called A because factor A is at the high level, B and C are at the low level. So whatever is high, we kind of indicate that. This is B and this is AB because A is high and B is high. Therefore, this is AB. This is BC because B is high and C is high. And the last one is ABC because all A, B, and C are set at their high values. Therefore, this experiment 8 would be labeled as ABC. Okay, so far so good. And I have kind of also indicated that the columns A, B, AC, and BC, I've asked you to fill it out yourself if you want to, because that is not important for our discussion here as of now. All right, so that is one thing I wanted to mention. And in the very last column, which I've drawn by hand, for some experiments I have put a tick mark, and for some experiments I've just put a circle, right? If you look at the table, the rows with the tick mark are also labeled in red color. So I've used red color fonts for experiments 2, 3, 5, and 8 in the table. And I've also indicated them with tick marks at the end. And the experiments 1, 4, 6, and 7, I have left them in black color font. And I've also just indicated them by empty circles in the last column. So if you look carefully, experiments 2, 3, 5, and 8 correspond to the setting where ABC is equal to +1. So whenever ABC was equal to +1, I've indicated them by red color fonts. So that means 2, 3, 5, and 8, these four experiments have ABC setting equals +1. And in complement, experiments 1, 4, 6, and 7 have ABC is equal to -1. So I have categorized them separately and I have just indicated them with black font. So we have a few things. If A, B, C is equal to +1, right? So that is 4 experiments are of that type. 4 experiments are of this type where ABC is equal to -1. All right. So I can also write it like 1 is equal to ABC, or I can say 1 is equal to -ABC. Why? Because this one I'm just writing it in this particular form. I'm just flipping the left and right hand sides. Here I'm doing the same thing. I'm flipping the left and right hand sides and also transferring the minus sign from the left side to the right side. I have not distorted anything. So I can write it as 1 is equal to ABC for the first for the experiments that are marked in red color. That means experiments 2, 3, 5, and 8. And for experiments 1, 4, 6, and 7, I can write 1 is equal to minus ABC. All right. So in general notation, I can write I is equal to ABC. You can treat 1 as an identity matrix if you like. I'm just saying we are replacing the symbol 1 with I. So I indicates 1. And the second part, we can say I is equal to minus ABC. This notation will be helpful later on. So I hope you understand the transitions. Experiments 2, 3, 5, and 8 have ABC is equal to plus 1. Experiments 1, 4, 6, and 7 have ABC is equal to minus 1. I can write ABC is equal to plus 1 as 1 is equal to ABC. I can write ABC is equal to minus 1 as 1 is equal to minus ABC. And in the next step, I'm conforming to the notation used in design of experiments literature, where I just replace 1 by I. Okay, so I is nothing like a symbol for 1. And this second equation becomes I is equal to minus ABC. So this is important as we go forward. And our claim is, if you have 3 factors A, B, and C, and you do not have the resources or time to do the full factorial design, which would comprise of 8 experiments. Let's say you don't have time to do it, but you have time and resources to do half of 2 to the power of 3. That means a fractional factorial design. The 3 factors should be there, but I want to do only half of the full factorial simply because I have resources only to do those 4 experiments. The question is, which 4 experiments out of these 8 are to be done? That means whenever you do less experiments, right, we have to be prepared for some loss in information. The question is, which 4 of the 8 experiments will lead us to the minimal loss in information? All right. So that is the central question that we ask. Out of these 8 experiments, if only 4 can be done, which 4 should be done? And I want to know something about the effects of A, B, and C. I cannot throw out B and then say, okay, we have only A and C, and therefore we can do 2 to the power of 2 design. So that's not the solution for this. We have to retain all the 3 factors, but can only still do 4 experiments. And the question is, which 4 should be done? Can we do experiments 1, 2, 3, and 4 because they are on the top of the table? Or do experiments 5, 6, 7, 8, which are on the bottom of the table? Are they the best set of 4 experiments? The answer is no. What we are claiming here is that you do experiments 2, 3, 5, and 8, or you do experiments 1, 4, 6, and 7. Either that set, the red set, or the black set. That will be the 4 experiments that leads to the best possible outcomes. If you can do only 4 experiments, those are the best 4 experiments to do. And we will argue why that is the case. Now, whatever is in this table, right? Exactly the same information I have put here. In fact, I've also filled out the AB column, AC column, and BC column, and I've rearranged it so that ABC is equal to plus 1. The 4 experiments go on top, and the 4 experiments with ABC is equal to minus 1 goes at the bottom. So it is exactly this table with filling up of AB column, AC column, and BC column, and also by rearranging the rows such that the experiments with ABC is equal to plus 1 is on the top, and the experiments with ABC is equal to minus 1 is on the bottom. And as stated on the slide, if you have to do only 4 experiments, you cannot do this full factorial design. The claim is this set of 4 experiments where ABC is equal to plus 1, or this set of 4 experiments where ABC is equal to minus 1 are the best half fractional factorial designs. That's the claim. Okay, and hopefully by the end of this video segment, we will understand why that is the case. Now, this is what we are trying to say here. We call this experiments where I is equal to plus ABC, or 1 is equal to plus ABC. That is called the principal fraction. The principal fraction experiments are those with ABC is equal to plus sign here. Those would correspond to labels A, B, C, and ABC, right? So if you take these 4 experiments in this table, in this experiment it is labeled A because A is kept at high and B and C are at low. The second experiment in this table, B is high, A and C are low, therefore this is labeled as B. The third experiment is labeled as C for the same reason, and A, B, C are all high, right? A, B, C are all high in this case, and therefore this is labeled as ABC. So the principal half fraction comprises of experiment with treatment combination A, B, C, and ABC. That is what is illustrated here, and the locations of those 4 experiments are also shown there, right? So this is experiment A. So this is factor A, this is factor B, and this is factor C. So low for factor C, high for factor C, low for factor A, high for factor A, low for factor B, high for factor B, right? So this experiment would be A, this experiment would be B, this experiment would have label C, this will have label ABC. So that is the principal fraction. The other part is called the alternate fraction, right? Where ABC is equal to -1, or you can write as I is equal to minus ABC. Those correspond to the 4 experiments that you see at the bottom of this table. So AB, AC, BC, and brackets 1. So those are the 4 experiments that are shown in these 4 corners. So you can do either this or you can do this. All right. So this is called the principal fraction because ABC is equal to +1. This is called the alternate fraction because ABC is equal to -1. All right. So this is in a diagrammatic form how we can illustrate or represent the fractional factorial. Now, this is a simple question. A certain system has 6 input factors, A, B, C, D, E, and F. The question is, 32 experiments were performed, and what kind of an experimental design is this? All right, so if you have 3 factors, so kindly see A comprises of 5s and 3s, right? So you have 3 representing low and 5 representing high, right? So that is what A is. And B can be batch 1 or batch 2. C can take values of either 6 or 14. 6 is low and 14 is high. D, which is the speed of something, that can take values of 6650 or 7350, right? Write down the table, only these 2 values are there. So 6650 corresponds to low and 7350 corresponds to high. Factor E can either take values of 5 or 20, so it's also tested at 2 levels. And factor F is or off or on, so it can only take 2 values again. So if you have 6 factors and you're testing each of them at 2 levels, you will have 2 to the power of 6 experiments that would constitute a full factorial, right? This will be a full factorial. So 2 to the power of 6 will be 64 experiments, right? For the full factorial design. But only 32 experiments out of this were performed, and that is what is listed here, right? The 32 experiments are listed there. So what you can conclude is that they have done half of 2 to the power of 6. So half fractional factorial design, right? So you can also represent it as 2 to the power of 6 minus 1 design. So people will understand that it is half fractional factorial of the full 2 to the power of 6 factorial. Okay, so that is what it means. So the answer would be, for example, 2 to the power of 6 minus 1. That is this design, or in words you can say it is half fractional factorial design for a full 2 to the power of 6 design. All right, so that is what it is. Now if somebody were to do only 16 experiments, right? So you're doing quarter fractional factorial design, right? If somebody were to do only 16 experiments, 16 is 1 by 4 times 2 to the power of 6, and therefore it will be 2 to the power of 6 minus 2 design. So you're doing quarter fractional factorial design. Okay, but for this particular question that is there, it is half fractional factorial design. Now, um, let us go a bit more into why we think those four experiments shown as the principal fraction where I is equal to ABC, or the alternate fraction where I is equal to minus ABC is considered to be the best option. All right, so that is where we are getting into, and for that we have to define a few concepts. Okay, so we have to define a concept called the generator, and we will do it by taking the principal fraction for our analysis. We could do a similar thing with the alternate fraction, but we will do it with the principal fraction. So we are going to consider treatment combinations that have a plus sign on ABC. So we are going to look at I is equal to ABC. That means ABC is equal to plus 1. All right. So this is called the generator. ABC, right? This thing is called the generator because I is equal to ABC will be called the defining relation. And just ABC, the right hand side of that, will be called a generator of this fractional factorial design. And what you also see from this table, going back to this table here, I'll erase the ink from the slides. So what you will see here is that, can you see in, let's say we look at the top four, BC equals A. Can you see that? In all the four experiments, BC is equal to A. This column and this column are identical. So we will say that A is aliased with BC, right? A and BC are aliases, right? So these effects will be confounded. You cannot separate these two, all right? Likewise, B and AC are aliases of each other, B and AC. Can you see that? The column B and AC are in fact identical. They are aliases of each other. So you cannot separate out the effects. And you can see the remainder, right? C and AB are aliases. So this is the loss we need to take. Because we are able to do only 4 experiments, we will lose some information. We cannot tease out all the direct and two-factor interaction effects separately. All right, we cannot tease them out separately because there is no free lunch. If you did 8 experiments, you could get out these effects separately. I can get the A effect separately, B effect separately, C separately, AB separately, AC separately, BC separately, and ABC separately. All right, that is what we would have had if we did the full factorial design. But because we are constrained to do only half of that, what is going to happen, as I stated earlier, is that we are going to suffer some loss in information or understanding about the system. And the loss is that we cannot distinguish the effects of A and BC separately. We cannot understand the effects of B and AC separately. We cannot understand the effects of C and AB separately. We can only understand the joint effect of A and BC. We can only understand the joint effect of B and AC. We can only understand the joint effect of C and AB. We can only understand the joint value of the constant and the coefficient of ABC, because you see I is equal to ABC, right? Directly means that this column of ABC and the column of ones are identical. So this stands for the constant term in the equation, all right, in your model equation. Therefore, you cannot tease out the intercept term in your model and the effect of ABC separately. All right, so there is going to be a loss because of this aliasing problem, which is unavoidable. But we can show that this is the best loss in information possible. All right, so sometime back, when I had my first ever Uber ride, the car got into an accident. All right, and I had a leg fracture. So I went to the doctor, and the doctor said, if you ever had to have a fracture, this is the best fracture one could have. So it's something like that. All right. Coming back to this again, right? So this is where we were, and then we said A is equal to BC. So this is the aliasing I was talking about. B is equal to AC, and C is equal to AB. So C is alias with AB, B is alias with AC, and A is alias with BC. And we all know I is equal to ABC happens to be the defining relation. Therefore, the constant term will be aliased with the parameter associated with the three-factor interaction. All right, so those are the kinds of things. We can also find the aliases. We don't have to go to the table and do it, as some of you may have guessed, from the defining relation or relations. Here we have only one defining relation because we are doing half factorial. If you're doing quarter factorial, you will have more defining relations. We can see that later. Okay, so here in this particular case that we are considering, we have the design relationship to be I is equal to ABC. And therefore, if I multiply both sides by A times I is A times BC, right? So I'm pre-multiplying both sides by A. I can also post-multiply, it doesn't matter. So A times I is like A times 1, so it is A is equal to A squared, right? So A is either plus 1 or minus 1. So A squared will always be plus 1. So we get A is equal to BC because A squared is equal to 1. So A is equal to BC, and that is what our alias is. So we get AI is A, that will be equal to BC. Likewise, you can show that by taking our defining relationship and multiplying it with B on both sides, you will get B is alias with AC and C is going to be alias with AB. Okay, now the question then would be, what if I had chosen some other design generator or some other design relationship, right? So that is what we are trying to see here. If AB were to be chosen as the design generator, right? That means the defining relationship would be I is equal to AB. Now, if I is equal to AB, what would have happened is, if I multiply both sides with A, so I will get AI is equal to A times AB, which would mean that A equals B. So what this design generator or this defining relationship would have given us is an alias between A and B. That is very dangerous because in any system, the direct effects are likely to be the most important. The two-factor interaction terms are going to be the next most important, and the three-factor interactions are going to be the next most important, and so on. So I would not want a design, an experimental design, where the direct effects are aliased with each other. I really want to find out the effect of A separately, the effect of B separately, and so on. All right. So this would be a bad design generator. This would be a bad design generator because it would lead to the direct effects getting aliased with each other. Whereas if you took this to be the defining relationship, a first order effect, right, is aliased with a second order effect. That's bad, but if you have to suffer loss in information, that is much better. A situation where the direct effects are aliased with second order effects is much better than a direct effect being aliased with another direct effect, like what would have happened in this particular case. All right, so this I is equal to ABC is a better defining relationship than I is equal to AB. So that is why the set of 4 experiments that we chose from this table, right, where with ABC is equal to plus 1, that is a better choice if we can do only 4 experiments in this 3-factor system. Okay, so if you have to construct a 2 to the power of 4 design, if you have to construct a 2 to the power of 4 minus 1 design, that means we have 4 factors, right? We have 4 factors A, B, C, and D. Full factorial will mean 2 to the power of 4 is equal to 16 experiments. This is full factorial. But unfortunately, I have resources only to do 8 experiments and I want to get the best out of the system. So how do I plan and design the 8 experiments? That is the question before us. So what you do is, if you have to do 2 to the power of 4 minus 1 design, or in other words, half of 2 to the power of 4 design, right? What you do is you start by writing a standard design matrix for the three factors. So here A, B, and C are the three factors that we will consider for starting. So standard form: minus plus minus plus minus plus minus plus for A, minus minus plus plus minus minus plus plus for B, four minuses followed by four pluses for C. So this is where you have. And then what you do is the best design relationship for the half factorial will be our defining relationship, or the design generator from consequently from that. So the best defining relationship would be I is equal to A, B, C, D. This would be the best defining relationship. Or in other words, we are saying the design generator should be A, B, C, D. Right? So this is the design generator, or this is the defining relationship. And we need to do only one defining relationship because we are going for half factorial. So it is 2 to the power of 4 minus 1. So this minus 1 indicates that we will have only to choose one defining relationship. And we choose it so that the constant term is aliased with the 4-factor interaction term. Okay, it will be deadly if we had the constant term aliased with a direct effect or a factor interaction effect and so on. So this would be a very good way to do it because it will generate aliases that are pretty good. Okay, so this will be the defining relationship. So if I is equal to A, B, C, D, if I multiply both sides with D, so I'll get DI is equal to D times A, B, C, D, and you have D times D, which is 1 plus 1, and therefore we also know that DI is nothing but D. D is nothing but A, B, C. So from this defining relationship, we can generate the column of D if D follows this relationship, right? So from here, you just multiply both sides by D, and then you realize that D times I is nothing but D. D times D is D squared is equal to 1. Therefore, you get D is equal to ABC. That is what is written here. So the column of D now will be equal to ABC. So A, B, and C are negative in the first experiment. Therefore, D is set to negative, which means low value for D. And for the second run there, indicated at the table, A is plus, that means high, B and C are minuses, that means B and C are at their low settings, and therefore D, which is going to be A times B times C, is going to be minus, is going to be plus. So in the second experiment, D will have a high value. So these are the 8 experiments that you have to do. For example, the 7th experiment in this table would have A to be low, B and C to be high, and D to be low. So that will be these meaning of the 7th experiment from the table. Of course, you have to do these experiments in random order, taking into account blocking of known sources of variability, etc., etc. Right? So those things are a given by now. So this is how you generate a 2 to the power of 4 minus 1 design. And this one will have this alias structure that I've written there, right? This one will have this alias structure because I is equal to ABCD. That's our defining relationship. And therefore, A multiplying by A on both sides will lead to A is equal to BCD. Multiplying both sides of this defining relationship by B will lead me to B is equal to ACD. Multiplying both sides by AB will lead to ABI is equal to AB multiplied by ABCD, right? So you have ABI, which will be AB because I is like 1. And then you will have A times A, which will be A squared. B times B will be B squared. And A squared and B squared are both equal to plus 1. Therefore, AB will be equal to CD. So that is what is indicated here. So this defining relationship will lead to this alias structure where the direct effects are aliased with the 3-factor interaction effects, and there's aliasing amongst the 2-factor interaction effects. All right, that means we cannot get the effect of A, B, and CD separately. We will be able to get the combined effect of A, B, and CD. All right, but because the A, B, C, D, the direct effects are probably the most important in any system, they are confounding with three-factor interaction terms is not going to bother us much more, right? It's not going to bother us a lot because these effects are typically small. I would expect BCD parameter, ACD parameter, ABD parameter, and ABC parameter to be small. And therefore, I will recover the ABCD effects fairly correctly because these are expected to be small. Okay, so if you have to take a loss, the question is what is the best possible loss to take? All right, so if I went for a design generate defining relationship which is I is equal to ABC, all right, then A will be aliased with BC, all right, B with AC, C will be aliased with AB. So this is dangerous compared to this because your first order or a direct effect is confounded with a two-factor interaction effect. These could be significant in systems. All right, so you're going to be in trouble if you do it this way. So this way is good. All right, that means if you define D is equal to ABC, that is probably going to be the best way for you to do the experiments. On the other hand, if you choose D is equal to AB, all right, so you can try and work it out what will happen if you chose your D column to be just A times B. Okay, that means your defining relationship is I is equal to ABD. If you do that, you can see right away you're aliasing a direct effect of D with a two-factor effect, which is going to be somewhat inconvenient because AB itself could be significant, D can be significant, so you're losing out on both sides. All right, so that's the general idea why D is equal to ABC is probably the best way to generate the D column and do the 8 experiments involving 4 factors. So I'm just continuing from here, right? 2 to the power of 4 minus 1 design. If I had done the full 16 experiments for the 4 factors, right? I could estimate 16 parameters if I wanted to. One constant term, B naught term in the model, 4 linear terms with coefficients beta, B1, B2, B3, and B4, 6 two-factor interaction terms, B5, B6, B7, B8, B9, and B10 as regression coefficients. And so these 4 parameters would correspond to coefficients of the 4 three-factor interaction terms. So ABC will be one of these interaction terms, ABD will be the next one, ACD will be the third one, and BCD will be the fourth one, right? So these are the 4 three-factor interaction terms that would be there. And one 4-factor term, the coefficient of which will be B15. So if you look at it, this is what I mean. When I say I can find a model relating the direct effects or the linear effects, the 2-factor interaction effects, all of them, all the 3-factor interaction effects, and the 4-factor interaction effect. So the parameters will be B0, B1, B2 all the way till B15. So there will be a total of 16 parameters, and since I have 16 experimental points, theoretically it's a tight fit, but I can estimate the 16 parameters. But unfortunately, I'm able to do only half of the number of experiments. So I'm doing a fractional factorial design, which kind of means that I'll have to take some sacrifices. And the sacrifices, we have already seen this, because A is aliased with BCD, A is aliased with BCD, B1 plus B14 is what I can estimate. I cannot estimate B1 separately and B14 separately. I can estimate only B1 plus B14. All right. So that is the idea. And I'm just hoping, because of the nature of systems, that the 3-factor interaction term will be less prominent or dominant compared to the direct effect. Therefore, I'm expecting B14 to be small compared to B1. And therefore, I'll be able to estimate the direct effect of A in a nice way. Similarly, B is aliased with ACD. Therefore, this is aliased with this. So I can only get B2 plus B13. I cannot tease out B2 and B13 separately. That's the information loss I've been talking about. And since, again, to repeat the same story, I expect the effect of ACD to be small compared to the effect of B. That's the nature of systems. All right. And therefore, B13 is expected to be small compared to B2. So I will not suffer a major loss in information, and so on. That's how the story goes. Okay, so this is how we construct a 2 to the power of 4 minus 1 design, and these are the ramifications of that. So I can represent the 2 to the power of 4 minus 1 design in this particular form, right? So I will leave you to figure this out on your own, but all you have to do is go to this table and understand that these are the 8 experiments that are shown there. This wing corresponds to the experiments where D is equal to plus 1 in this table. All right, D is equal to plus 1. That means runs 2, 3, 5, and 8 in this table. All right, and the left wing is for D is equal to minus 1 in that table. Okay, and you will understand, for example, when D is equal to minus 1, one of the experiments we do is with B and C being high, right? B, C means B and C are high. So D is equal to minus 1, B and C are high. Can we identify that thing here? D is equal to minus 1, B and C are high. So they're talking about this run number 7. That is that corner. Because B and C are high, A is low, this experiment would be D is equal to minus 1, and amongst A, B, C, this would be called label BC. So D is equal to minus 1 and BC, that is this experiment. So this is run 7 in that table, right, that you see. The values that are shown here, 80, 60, etc., correspond to the value of Y collected at those conditions. So that is what it means. All right. A 2 to the power of 5 design likewise can be constructed by starting with a full factorial design for factors A, B, C, and D, and then choosing I is equal to A, B, C, D, E as the defining relationship. If you choose I is equal to A, B, C, D, E as the defining relationship, if you multiply both sides by E, you will get E is equal to A, B, C, D. So the settings for E factor are going to be equal to the pattern which comes from A times B times C times D. So this is minus because A times B times C times D is plus 1 multiplied by minus 1 multiplied by minus 1 multiplied by minus 1 will be minus 1. So that is how you get the E design. And when you fill this E column, right, you get the half of 2 to the power of 5 design, right, which is 32 divided by 2, which is 16. So you are exploring 5 factors in using 16 experiments, half factorial, half fractional factorial. So you can also call this 2 to the power of 5 minus 1. Okay, and graphically you can show something like this. It gets complicated. What will you do when you have another variable called f, right? Let's say we want to do a 2 to the power of 6 minus 1 design. At some point in time, the graphics becomes more cumbersome or very difficult to manage, at least for some people, right? So we can just go with matrices, numbers, etc. So that is when the power of mathematics can be unleashed. So wherever visualization is possible, that's great. If it's not possible, we have to kind of have a leap of faith beyond a certain dimension, right? And then say, well, I know the general patterns that will emerge. So this is the idea, right? This is the complete table for that. So whatever you see in this slide in the form of the design table and in the form of those numbers is what is translated into this particular table here. All right. So these are the physical meaning of the factors. If anybody cares about that, it is probably related to something in the semiconductor manufacturing industry, right? And so they're looking at some yields as the output variable. So these are the values of the output variable. So for experiment number 5, for example, the settings are A is low, B is low, C is high, D is low and E is low, right? So this experiment would be called C. Why? Because out of A, B, C, D, only C is high, right? Out of A, B, C, D, E, only C is high, therefore it is labeled as C. And when you have these settings in for these variables, A, B, D and E are kept low and C is high, the yield comes out to be 16, and that's what is recorded there. Okay, so that is the table, and we can analyze this table. We can do the standard regression and try to find out the coefficient, etc., understanding that there will be aliasing, right? And by proper design, we have taken care of recovering the most important information to the best possible extent. That is what we are able to do by designing the fractional factorial using the design relationship. In this case, I is equal to A, B, C, D, E. All right, so in this table, I have shown the alias structure for this problem, right? Starting with the defining relationship, I've shown all the aliases there, and what you see is that the direct effects, right? The linear effects are associated with 4-factor interaction terms. So that is not dangerous because we expect the 4-factor interaction terms to have less effect on the output variables compared to the direct effects. So we are getting good information, right? And the 2-factor interaction effects are kind of confounded or aliased with the 3-factor interaction effects, okay, which kind of also is not bad for us because we expect the 3-factor interactions to be less important or less dominant compared to the 2-factor interaction effects. So this is what happens with the design relationship or the defining relationship that we have chosen. If you had chosen this as the generator, the defining relationship, that means ABC is the generator, then we know that E is equal to ABC. All right, because you take this defining relationship and then you multiply both sides by E, you're going to get E is equal to ABC and A is equal to BC, etc. So we are now bringing the direct effects closer to the 3-factor interaction terms, right? Which is a little more dangerous compared to the direct effects being aliased with the 4-factor interaction effects. Okay, so this is better than this. This is not as good. First, what you have here is the 2-factor interaction terms are aliased with other 2-factor interaction terms. That can be dangerous as well. Okay, so this is better than this. So I call this as a poor fractional factorial design. This is a better or the best fractional factorial design. All right, and what happens is, let's say you take this data and you analyze it. You build models, right? You build an appropriate model with 16 parameters because you have 16 experiments. So this is the constant term, and these are the different effects. So A, B, C, D, E. These are the direct effects. These are the 2-factor interaction effects, and these are the regression coefficients. So put it through stepwise or some tool like that, get this regression model, and what you will find is that the regression coefficients have this value. And if you go by the effects calculation method, your effects will be twice the value of the regression coefficient. So that we already know, right? For some reason, this table gives sum of squares. Maybe it is useful if you're doing some kind of analysis of what contributes the most, etc., right? So there is a correspondence. If you see the sum of squares is more, that term will be important. And that will also show in the regression coefficients. We can interpret things based on regression coefficients here because the inputs, all the columns, right, A, B, C, D, E, A, B, A, C, B, D, E, etc., are all confined between -1 and +1 because of our coding. So since all the variables are of the same size, I can look at the importance of terms just by observing the regression coefficients itself. When the variables in your problem are of very different sizes, it is dangerous to say some term is important or less important by just looking at the regression coefficients. Here we do not have this problem because we are working in coded variables and all the variables are of the same magnitude between -1 and +1, right? In fact, it has only two values, -1 or +1. So it's a very fair, even ground for all the variables, and therefore we can take a look at the regression coefficients and say which term is important or which term is not important. Okay, so we have to look at regression coefficients with care. Here we have exercise caution. And if you look at the numbers, this comes out to be the major thing. Leave the constant, right? That's there. That's good. But amongst the effects, this is the big effect. The second big effect is probably this. The third big effect is this. The fourth big effect is this. Others are all small. So what it shows, at least for this problem, is direct effects A, B, and C are important. And out of the two-factor interactions, only A-B interaction is important. And that is also corroborated by the fact that the sum of squares is high for the terms that come out to be important by just looking at the regression coefficients. Basically, we are saying that these factors are able to explain a lot of variation that you see in the Y data. That is what it means there. Okay, so in any case, A, B, C, and AB are important. So we started with 5 factors, A, B, C, D, and E. And now we are saying, after this analysis with a fractional factorial data, we are able to say that A, B, and C are the key things, right? A, B, and C. This interaction involves only A and B, so that's already there. So A, B, and C are most important. So what we can do is we can take this 2 to the power of 5 minus 1 design and throw away D and E, and then reduce it to a 2 to the power of 3 design picture with only factors A, B, and C showing up there. All right, and the 16 experiments, right, that we have done becomes a 2 to the power of 3 design with each experiment run twice. So that is what it is. All right, so this collapses, right? This 2 to the power of 5 minus 1 design collapses here, or projects itself into a 2 to the power of 3 design with replication, with complete replication, if you like. So why is this number 61.5? Because you have one experiment giving you 63 and a replicate giving 60. So 60 plus 63 divided by 2 is 61.5 in this illustration. This is 44.5 because one experiment gives 45, the other experiment gives you 44. All right, so basically you take the average of 45 and 44, that's where you get. And this is 32 for exactly the same reason. You can figure that out yourself, right? So and if you have, let's say this is 2 to the power of 3 minus 1 design. This is what I'm showing here because you have 3 factors, right? The cube, you have 3 factors, and you're doing only 4 experiments represented here, right? So let's say this is x1, this is let's say x2, and going from top to bottom is x3. These are 3 factors. All right, so you have these 4 experiments done for a 3-factor problem. So if you look at it from the top, right, if you're looking at it from the top, what you will see is you will see the data in the plane x1, x2, right, when you're looking from the top. So you can see the projection of the 4 experimental points into this x1, x2 space, right? And if you look at it from this side, what you will see is the data points in the x2, x3 axis. All right, so the 4 data points from the cube project into the 4 points on the corners of a square. And when you look at it from the front, you will see x1 versus x3, and the 4 data points from the corners of the cube project into the 4 experimental points on the corners of a square. So when you are able to remove a variable, when a variable can be removed, a fractional factorial design projects into a full factorial design. That is the idea. So in this case, if you're able to remove x2, this fractional factorial design becomes a full factorial design in x1, x3, in those variables. Let me stop here and I'll catch up with you in a next video. Thank you.